hilarious. All right, so it says two metal spheres are placed on the top of a wooden ramp. The spheres have identical masses and radii. The sphere 1 is hollow, and the mass is all contained in the outer shell, where sphere 2, in contrast, is solid and the mass is uniformly distributed throughout its volume. The two spheres are released at the same time and roll toward the bottom of the ramp. Which reaches the bottom first? Well, so let's draw this. I've got this sphere that's going down the ramp, and what was sphere 1? Sphere 2 in contrast is solid. So sphere 1 is hollow on the inside. So we'll call that sphere 1. And it's on a ramp. And we don't know what the mass is, but we'll just call it M. And then we have sphere 2. Same ramp, same ball, but this one is solid. And so that also has the same radius. And they don't tell us what they are. So this is sphere 1, this is sphere 2. And that has a mass and a radius, and they're the same. So then let's label what we know. So the spheres are released. They have potential energy that's converted to rotational and kinetic energy. So for sphere 1, the potential energy is the mass times the acceleration due to gravity. Remember, they both have the same height because they're on the same ramp. So that's H. From here to here is also H. So sphere 1, and then it has the kinetic energy, 1/2 times the mass times the velocity squared, plus the rotational energy, which is 1/2 times the moment of inertia times the angular speed. Now, if you simplify that, what we want to do is we want to convert that. Let me think here. On this last one, remember that inertia is equal to, of a rotational object, 2/3 times the mass, 2/3 times the mass of the object, times the radius squared, I think, if I remember right off the top of my head. So we're gonna sub that in. So for my moment of inertia, I'm just going to say 1/2 times 2/3 because it's hollow, right? And I don't know if we wrote that down very early on. So that's sphere 1. I'm going to write sphere 2 in a different color. So sphere 2 is essentially the same thing, with the only difference is that because it's solid, its potential energy, which is the same, and its kinetic energy would be the same because they have the same mass, except because it's solid, the rotational would be 2/5. The moment of inertia would be 2/5. Oh, I forgot to write something down, I see. R squared. And then this would be omega squared. And over here, this would be omega squared. I forgot to write that down. All right. So then sphere 2 has a smaller momentum of inertia. More of its potential energy will be converted So it will travel faster to the bottom. Oh, this is frustrating.
I never have time to do that in the morning unless I specifically wake up earlier to do that.
And so just so we're kind of clear, the potential energy, more of it is going to be converted to the kinetic energy because this one is lower, right? This is 0.4. What's 1/2 of 0.4? 0.2. Or this one is 0.6. So here I have a higher rotational energy, but a lower kinetic energy. This one will have a faster kinetic energy, but it'll take a little longer for this one to get rolling, but it'll have a faster kinetic energy. So sphere 2 will get down quicker. And that's it. Because they both have to have the same amount of potential energy.